Okay, let's get started. Welcome everyone to Arundel, the show where we look at the targetable database and try to understand from the first principles how can one build a modern distributed database which is cool in all different kinds of ways. Okay, again, we are on a streak of very in the trenches, very meaty looking at the code episodes. So let's dive right in. What we are looking right now is how the data actually moves from the database. So for the previous 30 something episodes, we kind of like, we were building a foundation. We were learning about all the building blocks to actually allow us, like, get some new requests from users, process them, and store to disk. And right now we are looking at how the process actually works. So last time, well, let's start even before that. Before last time, we were looking at the prefetch path. So again, the big idea in Target is batching. That although the purpose of Target is to process financial transactions, there is no process financial transaction operation in Target. There is only batched operations. There is, hey, here is 8,000 of transfers, please process them all at the same time. And one way in which Target exploits this batching is that instead of doing I/O for all 8,000 transfers sequentially, it does all I/O in parallel. So Target gets a batch of 8,000 transfers, it simultaneously loads from disk all relevant accounts, and once that finishes, it proceeds to execute the transfers sequentially. So in the episode before that, we were watching that prefetch path. How can we end up with all those potentially 16,000 accounts which are relevant for the 8,000 transfers already in memory by the time we start executing anything? Then last time we looked at the actual execution path, which now looks up those transfers from the in-memory cache map, hash map, then checks all the invariants that, hey, if you subtract amount from one account and add amount to the other account, you wouldn't overflow to zero, and you wouldn't overflow over the limit of accounts, etc., etc. I guess the key code which we looked at last time and which I want to revisit is the code to update indexes, because it's like really a really simple code, but it explains how you could get from something as simple as just a sorted list of values to something as rich as a relational model. So that is the idea. Whenever you update an object, you go and you update all the indexes related to that object. And to update the object, the key thing to update the indexes, the key thing you need is that you need an old version of an object. So if for your in-memory hash map, your update API takes just a new object, for something which implements relational model, you really need to pass both the old object and the new object. Because to update the indexes, you need to remove the value from the index which corresponds to the old object and add a value which corresponds to the new object. Okay, so throughout this whole updating infrastructure, one thing we kind of like hit but immediately dodge was this thing called object cache, which stores things in memory. And today I want to go and explain what this thing does. So first of all, objects cache is a cache, which means that it generally like holds accounts and transfers which were recently accessed. And that is kind of like, primary purpose of this thing. It enables performance. So if you end up transacting against the same small set of transfers, the same small set of accounts, all that small set will fit entirely inside an object's cache, and you would only access the disk to write the result afterwards. So you wouldn't incur like any read latency for executing transactions. But that is kind of like only one purpose of this thing. Another purpose is that it actually guaranteed to hold all those things which you will prefetch. So if we go back to our prefetch path, prefetch, what's it called? Prefetching queue. Yeah, if we go to the prefetch path, you see that, that the prefetch path ultimately results in us inserting a certain value into the object cache. And then if we go to the state machine, transfer, don't save. If we go to the state machine, we basically get these. We basically get this object from the object cache. And again, you see here we treat the absence of object in the object cache as a definitive statement that such object doesn't exist. So kind of like this is like very surprising. We call this thing cache, but actually we use it as if it is not a cache and as if it is like a real map which holds all the objects. So like what gives, like how could it be possible? And the answer is that yes, this is indeed not really a cache. This is a data structure which has a certain guarantee that the keys which you have inserted during prefetch are not going to be evicted until you are done with them. So, but at the same time, it is kind of like still a cache. It like cannot hold all the objects in the database because obviously your disk size might be much larger than your RAM size. So like somehow this has to work. Okay, so how could we implement this thing, and like what is like more precisely the contract? So I guess it's useful to take a look at how this is implemented. And the idea for this data structure is inspired by some academic paper about Kuku-Hashing, which described a structure where you have a hash map, and alongside this hash map, you have a stash. So kind of like the idea of Kuku-Hashing is that you kind of like insert a value, and it always evicts another value, and then you evict another value like somewhere, and like eventually stuff might fall off a hash table. And the idea of a hash, the idea of a stash, is that you have like this like cache, and you insert things into the cache, and sometimes things fall out of the cache. They get evicted because they weren't recently used, but then you catch them inside the stash. And that way you guarantee that you still hold on to the value. Like right now, this kind of like sounds useless because, well, why don't you, like, if you always keep things inside the stash, then why don't you just always use the stash and get rid of the cache part at all? But the thing here is that periodically, once you are sure that you are no longer in the need of those stashed values, you could actually clear that stash. And this is actually how this data structure is going to be set up. So let's see this. Okay, I realize that I am explaining this in a rather confusing way, and well, I wish I could explain it better, but I can't, so you have to bear with me. Okay, yeah. So the core, it would be so great if DSQL had a shortcut for folding all the functions, which it doesn't have because it's not that good of an editor. Okay, I guess I should use split screen. So I want options here, and here I was compact. Okay, yeah. So the two key things for understanding the data structure is this option structure and this compact. So options. Options declare the capacity of the data structure. The map field defines the size of a cache. Okay, no, I've lied to you. Obviously, the cache value defines the size of a cache. So this is values which you might or might not cache, values which might incur cache misses. And like this is like a very large number, like millions. Then you have map value count max. This is the count which determines the amount of structs which have to have a guarantee that they are there, that they cannot get evicted. So this is typically just thousands. And then there is this compact call which clears all the values which were persisted in the stash. So the workflow is like this. You start with an empty cache map. Then you like do a bunch of inserts. And as long as you did less than map value count max inserts, you have a guarantee that all values are still in your cache map. And you also have a requirement that before you exceed that amount of inserted values, you actually go and have to call this compact method to clear the stash, at which point the values might be gone, and then you might insert new values. So how we're going to be using that for our state machine is, well, that's simple. We have a bunch of 8,000 transfers. So we know that 8,000 transfers corresponds to 16 thousands of accounts because each transfer has 2 accounts. So we need to initialize a cache map, which is guaranteed to store 16 thousands of accounts in its stash. Then we just use it for a single batch of accounts. And then at the end, we are calling compact to release the memory and to prepare it for the next batch of accounts. So I guess the most interesting thing here is to trace how we thread these like two, well, kind of like the cache value max is like not a crucial parameter. Like if you get it wrong, your code is just going to run slower. It wouldn't be incorrect. But the scope value max is like crucial. You have to get that correct. Otherwise, the map value count max, you have to get it correct. Otherwise, at some point you might evict something which you shouldn't have evicted. And then in the state machine, you would treat that as an absence of value. Okay, so let's try to reverse track this. So this cache map type is what our object cache is. And as usual, the standard pattern, generic types in Zeek are implemented using functions which are parameterized by types and return type. And the target specific naming convention here is that such generic type constructor functions have type in their name. So we have cache map type. When we create an object cache, we say that hey, object cache is a cache map type for parameterized with the key, which is the primary key of our object, and with an object, which is like an account and transfer, and parameterized with specific functions for hashing and comparing objects. Oh, by the way, that's actually curious. This is, I think, the first time where we have hashing. Well, it's not the first time; it's the second time, because the first time we already saw that in the set associative cache for the grid cache. But basically, this is kind of like curious because data on disk is sorted, and we use essentially like ported array to access it and binary search. But in memory, to speed up point lookups, we are actually using a hash table. So this is again a case where a single data like account is indexed both by sorted index, so by like the order of IDs, as well as by the hash. Okay, so how do we actually init this object cache? As a reminder, I love reminders. Well, sorry. There are only 2 notable objects in Target: accounts and transfers. And internally, each object is actually exploded on disk into several, quite a lot of actually, LSM trees. Because one tree called object tree stores objects themselves, keyed by user supplied ID. Then we have ID tree, which stores IDs keyed by automatically assigned timestamps. And then for each field over which we want to have an index, we also have an index for that tree. We also have a tree for that index. All the trees related to a single object are grouped in the grove, like this is grove on the left-hand side. And the object cache lives, because it caches the entire object, it lives at the groove level. Okay, so we pass cache entries max here, and okay, this is this is actually interesting. This is something we potentially could optimize that. So I told you that, like, you know, we can reset our cache map after every batch of transfers. So it looks like we do this slightly rarer than that. Well, not slightly, like 32 times less frequently. And this, I think, is actually more or less accidental, or maybe not, but we'll get to that once we get to compaction. Okay, I really hate to really talk about this right now because we are not there yet, but okay. Compaction. Compaction is the process of, like, taking some trees from some levels in your LSM tree, squishing them together, removing the values which you are no longer need due to the fact that earlier levels in the tree shadow later levels, and then writing the resultant smaller compacted tree somewhere. At TigerBeetle, compaction operates on so-called compaction interval, or like LSM batch multiple. So LSM batch multiple is 32, and that basically means that after 32 batches of transfers, where each batch of transfers is 8,000 batches, so it's going to be like 250,000 transfers or something like that. After like this many transfers, we go and like start this compaction process, and finish this compaction process, LSM batch multiple times later. And for some reason, we actually want this object cache to persist objects in the stash up to this entire compaction interval, and not just a single batch of transfers. But that's kind of like not really interesting. Okay, so how many transfers we are going to persist? Well, that's the multiplier, and then we want to count how many values in the batch we could have, and separately, okay, so batch value count limit counts like the amount of objects you could modify, and this prefetch for read counts the amount of objects you want to read without necessarily modifying them. Okay, and this whole thing is created in the state machine. Well, no, it's worse. It's created in the forest. So, because forest has several groves, and when we call forest.init, we are passing yeah, we are passing growth options, and we get growth options from init we pass to the forest. So let's go to the state machine and try to peel through. Okay, through this whole thing. Okay, we have forest. Do we store forest? We should be storing forest. Who is the forest? Okay. Do we initialize forest? Okay, yeah, apparently we do. So here we are initializing forest, and here are the forest options. Okay, so fine. Okay, so this is batch value count. Limit is the thing which going to end up here. And how does it work? Okay, so batch value limits. Okay, I think what is batch value count limit? Okay, so we have like our batch of transfers, which is this many bytes long. Now we divide the size by the size of the transfer object to get the maximum number of transfers inside a single batch. So this is this is the amount of transfers we get. And then for each field, we say how much mutations could be in a single batch. So for transfers is like simple because, well, kind of like one create transfer event produces just one transfer. So then this gets up all the way here. Batch transfers limit. Okay, it's okay. This is like a bit of code which I'm not super proud about Target because yeah, it's kind of like crucial that we get all these limits right, but it's actually kind of like hard to follow. Okay, so tree objects transfer timestamp. For update. Wait, where do we use prefetch for update, prefetch for read? Okay. Now I think I now understand better. Okay, so like we want to prefetch entries, and apparently we want to define which entries are prefetched for updating. So when we create something, and which entries are prefetched only as a read-only. Because we have pending posting mechanism for transfers, it might actually, yeah, be the case that, hey, we are prefetching transfer just for read it without updating. So that's why we have to. Okay, so I'm kind of like, okay, this probably makes sense for someone who already is familiar with Target, but not for you, so let me try to explain. So basically, we have a mechanism in Target to create the so-called pending transfer, which requires a separate transfer to actually, enable it. And that means that the worst case is that the first batch is all the pending transfers, and the second batch is the posted transfers for all the pending transfers. So for the second batch, you actually would need twice as you would need to prefetch 16,000 transfers, because you would need for each transfer which posts or void a pending transfer, you need to prefetch it to make sure that it doesn't exist, so that you don't have so that you have an idempotency, and then you would actually have to fetch the transfer which is being posted or voided to like check that, hey, actually it hasn't expired or something like that. So that's why we have both of these here, and when we create prefetch keys, we size them by the sum of this. So okay, I understand this. The only problem is that this isn't what I was trying to understand. I was trying to understand this value count max. Like, why do we do prefetch for read, and then we do batch value count limit? What is batch value count limit? The amount of create and then read. Well, okay, yeah, right. It makes sense. Again, for the case where the first batch is all the pending transfers and the second batch is all the posted transfers, well, the second batch adds up creating these many transfers, and we want to keep them in memory, obviously, and then it also adds up reading this amount of transfers. And I guess prefetch for update is counted into this sort of code. So again, kind of like it's it's kind of like hard to understand what's going on here, and like you really need to go and like read the code specifically. And like the only like embarrassing fact here is that I think it was me who like introduced it, this split into prefetch for read and prefetch for update, which I now can make heads or tails. But I think kind of like we like got like the basic idea. So we look at our like the question we are answering here is, okay, so we are like submitting a batch of transactions. What is the worst case of amount of objects in memory we might need to introduce? We might need to process this. And kind of like, our first thinking is that, okay, so we have create accounts, and each account is like 256 bytes. So the total amount of accounts in in a single batch is the size of a batch divided by the size of account, which tallies up to 8,000 transfers. And we could say, okay, so that our objects cache have to hold 8K. But then wait a second, but there are also prefetch transfers and pending transfers and posted transfers. And when we post a pending transfer, we actually need to keep two transfers in memory: the posting transfer itself and the transfer which was originally pending and which we are posting or voiding. So actually we kind of like need to double that amount, and this plus does exactly that. Okay, so that I think kind of like explains the general idea. So we have this cache map. It has a cache, and besides the cache, it has a stash, and the stash is sized for this amount of values. So whenever we insert something into the cache, and then this value falls off the cache, we put it into the stash. And as long as we insert smaller than this amount, then smaller than this amount of values are going to get evicted, and they all end up being in the stash, which guarantees us that none of the values we have just inserted was evicted, which is exactly the guarantee we wanted to have. At the end, we are going to call, like once we processed all those batches and we no longer need all those objects in memory, we call compact, which will clear the stash, which will allow us to insert the next batch of items into our object cache. Okay, now we'll look at the actual implementation. But before that, I want to cover another state machine feature, which we kind of like glossed over. So let's start with our transfer object. You see in our transfers, we have this linked flag. Okay, yeah, we have flags, and one of the flags is linked. So semantic of a linked flag is that it allows you to create a transaction out of several transfers. So you could have like 5 transfers, then you can link them to each other, and if any of the transfers fail, then the results of all the previous transfers are going to be rolled back. So the idea here is that for a set of linked transfers, either all of them succeed at the same time or none of them succeed in the same time. And that actually is an interesting primitive you could use to implement distributed locks, account limits, and like whatever you want. So the way we implement this in the state machine is by using these scoped things. So this is a function which executes. It takes a bunch of events and then executes each of the events. So first we like go and cast this batch to like slice of transfers or slice of accounts. And then while the bulk of execution is handled by this like create single transfer, create single account code, on top of that, we have this generic code to handle linked chains. And the idea here is whenever we start a linked chain, so if the current transfer is linked to the next one and we don't have a chain right now, Then we create a scope and open scope. And after we executed a particular transfer, if it failed, and if we have a chain, then we have scope close operation, which rolls back the chain. And this is also something which is handled by which needs to be handled by the object cache. So you see in the implementation of scope open, we just open the scope for each corresponding growth. And in the growth, when we open something, we open scopes for each of the trees, and we'll get to how scopes work in the trees next time. But crucially, we also open scope for the cache map, which is just says that scope is open. So okay, that is I think all there is to the API of the cache map. And now let's look at the implementation. So again, our idea is like we are a cache, but we are forbidden from forgetting map value count max values since the last time we were compacted. And we also have this scope thing where we might want to do a certain amount of modifications. But if the caller says that, hey, actually, like, you know, like those like 128 previous modifications you did it, they won't forget about them, we need to be able to roll back. Okay, let's see how this works. Again, the fields. We have cache and we have the stash. The cache is like this optimistic cache, and the stash is something which provides guarantees. Yeah, apparently for some things, having a cache doesn't really make sense. So probably those are going to be like, you know, write-only things. So the cache is optional. The stash is required because, well, you have to use it for the prefetch anyway. And then we have a rollback log. So like when we, if the scope is active and we do some modification, we record the previous value in the rollback log so that we could restore it. When we initialize ourselves, again, as usual, cache is initialized according to the number of values we want to cache. And well, I kind of like glossed this over, but the cache is our familiar set associative cache, which we also use for grid cache, which we covered in one of the previous episodes. So again, kind of like useful reminder, like why do we have like two caches? It is because one is a grid cache and another is object cache. So grid cache caches raw blocks on disk. Object cache caches accounts and transfers. And the relationship here is that a single grid block holds many transfers or many accounts. And if you, and it might be the case that you want to cache only a single account from the entire grid block. So while in theory it is possible to only cache the underlying grid blocks, it is useful to cache accounts separately because you could reduce memory usage. Like if some grid block has only some accounts hot, then you could keep only those accounts in the cache. The second reason why we do this double caching is that because, as I've said earlier today, in the grid cache, the data is fundamentally sorted. So the lookup there is binary search, which is logarithmic. In cache map, the objects are hash. So lookup there is a hash map lookup, which is generally faster than binary search over large arrays. Okay. And the map is just a hash map with a specific capacity. So, okay, for cache, we pass the desired capacity. and for map we also pass the desired capacity. Again, the standard targetable pattern, which is repeated over and over and over again. Init function takes allocator. This allocator is passed down to the init functions of all the data structures, which do the allocation in the init. But we don't actually store this allocator, and this allocator goes away. So in all other functions like get, has, absurd, remove, whatever, they don't have access to allocator, so they statically are forbidden from allocated. And for the rollback scope, well, the worst case is okay. So I was going to say that the worst case is that how many values we could create, but actually here, so remember, this value counts the entire LSM batch multiple of prepares, and for rollback we really want to, like, the worst case is that we are is that all transfers in a batch are linked, and we roll back the entire batch of transfers, but nothing more. So that's why this is smaller. And okay, let's go back and see how this is initialized. So it is initialized by batch value count limit. Yeah, which is exactly what is expected. And here, as a reminder, like why we need those two separate is that because we multiply this here. And again, I don't think like it is like super physically required to multiply here. I think, like, you know, with some extra legwork, it should be possible to get rid of this multiplicator. Would actually reduce our memory usage quite a lot, but well, we'll get to it once we'll get to it. Okay, so allocated, bam, done. Then the allocation, simple, the same as allocation, except that usually we do it in the reverse order. Well, the same here. So rollback local allocated last. So let's delete rollback allocated first as well, etc., etc. Okay, this is actually kind of like, you know, like this is a bit of language trivia. When you have variables on the stack, then in general, like the standard pattern is initialization, well, deinitialization is going to happen in the reverse order of initialization. So you create A, B, and C, and you destroy C, B, and A. When it comes to the struct fields, the situation is actually a little bit murky. So for TagCapital, we also try to stick by default to this reverse order. But it's curious that Rust actually doesn't do this. In Rust, the init order of struct fields is the same as the init order. And like the reason why we need the reverse order in Zeek is that in Zeek sometimes, like, you know, you initialized one struct field, and then in another struct field you use the value of like this previous field. So kind of like it's helpful to delimit them in the opposite order. In Rust, you generally don't have this structure where one field depends on the other field, because that's just straight out forbidden from a borrow checker. So like you could just delimit in the natural order. And to verify, this is not what's happening right here. So right here, you could basically write them like in, like, you know, in some random order. Like you might, I don't know, maybe like even in runtime, look at random number generator and generate it in random order. But like, I mean, you need to pick some order, and reverse order is like the standard one. Okay, so let's see something simple. How has and get works. Well, has is just get. And get, again, we look up in the cache, and if there's nothing in the cache, we go and look up in the cache. But I don't understand why we do this timestone thing here. It makes zero sense for me. Why do we okay. Okay, this looks super weird to me. I would totally expect this to read just get pointer key because, well, tombstone from key. What is happening here? Oh, oh dear. Is this really how it works? Okay. Yeah. Okay. Okay. I think I got it. So again, uh, as usual, as usual. When we talk about hash map, like normally, like in high-level programming language, you have like your key in a hash map and your value in the your value in the hash map, and you map keys to values. If you write low-level code, then what you would realize is that most of the time you don't have a separate key and a value. A key is just a part of the value. It is a field inside the value itself. So rather than using a hash map, what you actually want is that you want to use a hash set which is keyed by the value of the field. So that's why for our map, we use a hash map where the key is the entire value and the value is void. And then when we compare to values, which are keys, then we only extract the key bits out of this value and compare that. Now, when we want to get a key, we want to use hash map API, Zeek standard hash map API, and that requires us to pass the entire value. So we need to come up with arbitrary value which matches the current key, which we use this tombstone function. That feels like not how you should be doing this because I think this git key adapted probably is a better way to do this. How does it work? Context. But yeah, it's kind of it feels like it's really should be get key picture adapted, and we should pass key, and we should pass the context for our hash map, which is like this. This whole key, but well, kind of that's a lot to write, so we just use this tombstone hack, which I guess kind of is a lesson that we probably should create our wrapper around hashmap APIs, which actually optimizes for the common, or I would dare even say the single use case we have for hashmap in TigerBeetle. That is when keys and values are actually exactly identical. Okay, so now that I'm no longer confused, this code again makes sense to me. So if we have a cache, then we look up value in the cache, which might either return a value, in which case, well, it's the value, or it might return null, which means that either this is just a cache miss, but the value is still in the stash, or that there's genuinely no such value in the cache map. So if we got a null out of our cache, or if there isn't cache, then we go and do a single same lookup in the stash. That's easy. Okay, so let's look at something more fun. How do we update value? And here we have upsort function. So upsort is a portmanteau of update and insert. So this function which can either update value or it can insert a new value. And again, as usual, in high level semantics, you usually just like call it insert, and be done. But for us, like often, like well, most of the time, we actually need to distinguish between those two cases, are whether you're inserting a new value or whether you are updating an old value. But in the case of a hash map, that's actually not really needed. That's why we have a single upsert. Okay. First, I guess we go and look up whether we have okay. This is how it works. First, we insert a value, and then we update the scopes. What happens? How could? Okay, that's nice. I didn't realize this such feature exists, but apparently, if I wiggle my mouse vigorously, the cursor grows bigger. Okay, that's nice. So absurd. Like, well, we insert value, and we get the old value back. And then, if the scope is active, we need to like add something to our rollback log so that we could undo this upsert later. So, okay, if the scope is active and we actually, there was some old value which we updated, then we insert this old value into our rollback log. If there wasn't an old value, then during update, we need to remove this value. So we go and insert a tombstone for this key. And let's actually look at the rollback code. Rollback. I think it's called scope close. Okay, yeah. So scope close. If we scope close and we say scope close persist, so we actually do want to persist all the changes, we just say, okay, let's clear the rollback log. If we do want to do the undo, then we go through the rollback log in the reverse order. And if the value is a tombstone, so there wasn't previous value, we go and remove this value from the cache and from the stash. Otherwise, we should go and insert it back. So we call upsert. Okay, so that's like standard undo redo functionality. Okay, so we kind of like we learned how to undo things, but we haven't yet learned how to actually do things. But it's kind of it's a safer way to do this. Like once you know how you can undo something, then you can go and try to do this, because well, if you mess up, then you can undo. On the other hand, if you start with doing something and then you realize, oh dear, I wish I didn't do that, but you don't know how to undo, then well, you kind of like have to remove something, maybe like clone repository again, maybe even like reinstall your Arch Linux. So yeah, starting with an undo is safe. Okay, so sorry for dead jokes. Okay, so how do we insert value and return the value of the old value which was there? Well, I guess again, two cases: we either have the cache or we don't have the cache. If we don't have a cache, that's like trivial. We just go and insert directly. Well, I was thinking that we were directly inserting into. Well, yeah, we are going to directly insert in our stash, which is just hashmap. So we look up the value there. If we found the value. Wait, what happens here? We should be returning. Wait. I don't. I don't like this at all because this should be. Hey, this is okay. This sounds like a bug to me. Uh, okay, okay. So this is strange because if I'm reading the code correctly, we are expected to return the old value in the case of the update. But here, what we are doing, oh, okay, okay, right, okay, it's smart code, Dampman Cloud, I didn't understand it. Okay, so this is like, this defer is like really critical. So when we assert something, we return, if we found existing, we return the old value. And then we update the old value with the new value in defer. So after this dereference is evaluated, which is exactly how it actually should be written. Like that's a idiomatic, and that's like how you kind of like not only see like what is happening, but you see like, you really see the intention of the code here. But well, if you are like slightly nervous because you are on the stream and you miss this defer keyword, then well, you are going to embarrass yourself in front of like 53 people. Okay, so now that we have dealt with the easy case where we don't have a cache, let's figure out how to handle the hard case. We have a cache. Okay, so first of all, we like go and insert result in our cache, which might or might not evict a value. And this is okay. This is like complicated. So here we are operating with a map, and when we insert something, what we get back is the old value for this key. In the case of a stash, we kind of like might actually evict a different value, and we'll have to deal. In the case of a cache, when we assert a value, the value we get back is not necessarily like the value of the same key. It might be the like unrelated value which got evicted, so we have to deal with it somehow. Okay, but the simple case is that we insert something, the cache was like completely empty, so we didn't evict anything. We just inserted insert a new value. So, okay, should we return null here? Well, not really, because again, remember we have like two-level data structure where we have stuff in the cache and stuff in the stash. So we know that for cache, it was a genuine insert, but the old version of this thing could have been in the stash. So that's why we here go and return, remove it from the stash, return it. Now the hard, like the hard case of a hard case. We insert something into the cache, and we get some value evicted from the cache. Okay, if we evicted some value, and we also updated the value in place, so we evicted the value for the same key, so that like the evicted value is actually the old value. Then we just return it. Otherwise, if we evicted, but our value was unsorted, that means that we have evicted unrelated value. So evictee is not a value which we should insert. Moreover, this is the value which we actually should preserve in our stash because that's our contract. So in this case, we go and insert it in our stash. And I guess this is also the case where we fall through to removal from the stash, which makes sense because Oh, maybe not. Okay, should we... Could it be the case that the value is like both in the cache and also in the stash? I guess probably not. So we inserted, it was new, but well, yeah, okay, inserted, it was new in the cache, but it still might have been in the stash. So we just have to try to remove it from the stash. Okay, so that kind of like it. Again, it's like slightly like, you know, 3 different cases where you have like stash, cache, and scopes, and it's like slightly hard to wrap your head around this code like immediately. But like if you spend like 15 minutes meditating about it, you realize that it's probably correct. Okay, so let's say that we've dealt with fetch, which I think was actually like the hard operation. So for the removal, okay, we remove stuff from the cache. There is no stash handling because we need stash when we like evict something from a cache, and when we remove things, well, there's nothing to remove from a cache because you just got more space. So the removal case is like comparatively easy. Remove from the cache, and then remove from the stash. And then if we remove something, then we go and add it to our rollback log. Then scope open, scope close. I think we kind of basically discuss them. So scope open, just we mark scope is open. Scope close, we go through our rollback log in reverse direction and append things, which I think basically concludes the story of the cache map. So again, let's summarize as per our usual tradition. Cache map. So it's kind of like a cross between a cache and a map. And it serves 2 purposes. First of all, it should cache as much values as it can probabilistically. So it should make some heuristic decision about which values should be cached and which values should be evicted, to try to keep as much values which are going to be relevant in the future in memory. And the map part. The map part. The map part is that it should guarantee that the recent few values which were modified for the cache map interface are there. So it's kind of like, you know, it's a bounded guarantee. Your cache map, like your standard map, okay, it's very confusing. So your cache basically gives you 0 guarantees whether something survives or not. So you could insert foo in the cache, then you can insert bar in the cache, and if there is a collision, the next time you look up for foo and it's not there. The map kind of like guarantees that it's always there. So you insert foo, you insert bar, then 1 billion operations happens, you look up foo, foo is there. Here we need only bounded guarantees. We need a statement something like this. So if you inserted a value into cache map less than 1 million inserts ago, then it is there. Otherwise, it is allowed to expire. The reason why we need this guarantee is that for prefetch, we only need to deal with a small number of batches of transfers. So we only care that the recent items should be guaranteed to be in the cache, and if they exist, but for all the other items, it's like okay if they are only probabilistically there. The way we implement the cache map is like pretty directly. There is a cache and there is a map, and the job of the map is to catch all the values which fall out of the cache. And every so often, the map is cleared by the compact operation. So I guess we haven't looked at the compact, but it's like super trivial. Just go and clear the map, which we call the stash, because it all comes from the paper which introduced hash maps with a stash. Okay, one extra complication is that we also want to use this data structure to implement linked transfers. To say something like, okay, HashMap, like please do these 10 operations, but in the middle, we might actually change our mind and say, hey, actually, we wish those 10 operations that didn't happen, and then you need to cleanly revert the effects of all those things. And that's exactly like the scope mechanism. So if the scope is open, which is actually not the expected case. In an expected case, you shouldn't have a scope. But if the scope is open, this data structure maintains an extra undo log. And if the scope is reverted, we go through the undo log and, well, undo everything we wanted to do. And that completes the cache map. So I guess next time we are going to go even closer to the compaction proper, and we'll look at how table mutable and table immutable are set up in the table. And the next time is going to be exactly 1 week minus 1 hour later at 5 p.m. UTC on Thursday, live on Twitch. And if you miss that, you could always watch a recording on YouTube. Thanks again for joining, and see you next week.